Good day. Welcome back to the Computer Science 144 video lectures. So in the past couple of weeks we have spent time discussing object-oriented programming. So if you remember correctly, we started in the first week. We discussed how you would create, not create your own data types, but how you would use data types that has been created by someone else. How would you use that in your own code? Then in the subsequent week, we start using those data types that we've seen how other people created, and we created our own data types. In other words, in the first week we used the data types, in the second week we created the data types. Then thereafter, in the week thereafter, we discussed then how you would design these data types. Remember, I said that the design of these data types is not an easy task, but it's something that you learn over time. And we end then our lectures with in-body simulation, where we put all the things that we've discussed so far into practice. Now today we start with a new set of lectures where we would analyze and discuss algorithms and data structures. Now these data structures and algorithms that we discussed, they form the fundamentals and the fundamental data structures they are for computer science, and also for all the applications that we've seen out there in the real world. They actually consist of a body of work that's roughly been accumulated over the past 50 years. And they are really everywhere. And the important thing about knowing these things is they can differentiate you between just writing a simple program that you won't be able to deploy to big servers or big services to many people, but would allow you to really do a lot of big stuff. For example, if these things weren't existing, you wouldn't have seen Google, Amazon, all the big companies. An iPod would not exist. My computer would not do all the fancy stuff I want to do. So they really form the heart of our algorithms and things that we use in the real life. So the topic, if we look at the book, is indeed data structures and algorithms. That's chapter 4. And in particular, we start today with performance. Now, why performance? Well, I've said that we will discuss some new data structures and algorithms in the next couple of weeks. But the question is, how would you differentiate between a good and a bad algorithm? How would you know that the one is doing better than the other? And so the aim of these lectures that we will present this week is to look at how would I classify an algorithm as one as being better than the other, and in a sense do a performance. We will see how we can measure that empirically by running, in a sense, a stopwatch. And we will also show that we can do it with mathematics. So we will have two approaches to measure the performance of algorithms, one empirically, the other mathematically, and that will be the study for the next couple of lectures. Now, interestingly enough, this started a long time ago, long before a computer existed, with Charles Babbage. Now, Charles Babbage was an English mathematician. He was born on the 26th of December 1791, died on 18 October 1871, and he was indeed an English mathematician, philosopher, inventor, and a mechanical engineer, and he also developed the idea of an analytical engine. Now, the analytical engine is a mechanical computer, and it's sort of the idea of a programmable computer as well. So he's sort of the father, you could say, of the modern programmable computer. And in that time he had the following statement: as soon as an analytic engine exists, it will necessarily guide the future course of the science. When any result is sought by its aid, the question will arrive: by what course of calculation can these results be arrived at by the machine in the shortest time? So clearly he is referring here also to some form of performance, and that's definitely the idea that we will use. We want to answer, in a sense, the question: by what course of calculations can these results be arrived at by the machine in the shortest time? Now, so the challenge that we have in this course at the moment is will my program be able to solve large practical problems? That's the question that we want to answer. And remember the strategy that we have with computer programs is that you usually write your program, you compile it, and that's the first step that you have to get right. And at this point, you should be able to compile a program without a problem. And after you've compiled a program, usually you have a mistake or two, and then you do some debugging. And if you think of it, it's a slightly higher hurdle that you have to overcome. And then the next step that you ask is, can this thing solve problems? Can it solve bigger problems? Can it solve the problems in practice? And this is what we're trying to do. Now, this analyzation of algorithms that we will discuss in these lectures originated with Knuth in the 1970s. So Donald Knuth is also one of the fathers of the modern computer science that we have. And he came with a key insight that we should use a scientific method to understand performance. So that means we should look at the scientific method. So the scientific method has 5 steps, as I've outlined over there. Of course, I will just discuss the basics of the scientific method. You can find books in the library and other places that will describe the scientific method in even more detail. So the first step is you would observe some feature of the world, and then you would make an hypothesis, basically saying what you think is a model for your observations that you're doing. Thereafter, you would predict using this hypothesis. In a sense, you could design experiments using this hypothesis, and then you can verify the predictions by making further observations. So if your hypothesis is predicting something, and you can then verify that by actually making the observation, and then as good scientists, you will validate that at the end by repeating things, make a better hypothesis, and see if there are cases where the things don't agree or disagree. So as an example, I can think of the following. Say, for example, you taste your food, and the food has not a good taste. It's maybe this bland taste, and you're a bit unsure about that. So then you can make an hypothesis and say, well, maybe I don't have enough salt. So you could say the problem is salt. I should add more salt to the food. Of course, at that point, you can make a prediction. So you can argue that if I add more salt to my food, then the food should taste better. Now you have designed, in a sense, an experiment, since you should taste the food in order to verify that the food is indeed tasting better. So you verify the hypothesis by tasting the food. Now at this point, one of two things can happen. The food can taste better, in which case you could argue that, well, indeed, maybe salt was the problem. In a sense, with the hypothesis, you can never prove it completely, since, I mean, it could just be, well, that you add a bit of salt and then you realize it's not doing the job really quite right. So and that's why there's also this validation step towards the end, where you can actually taste again. Maybe you need add some other spices or something. I don't know what you want to eat and how you like your food. But the point here is we start with the hypothesis, that is, I don't like the food. Well, that's not the hypothesis. I don't like the food. That's the observation. Hypothesize, I should add salt. Prediction, now the food should taste better. I can verify. In other words, I have an experiment. So I taste the food, and it will either taste better or not taste better. And then I will validate it and rethink of things. Important thing is that an experiment should be reproducible. So if you do the experiment today, you should be able to do the experiment tomorrow. So maybe the food example, it's a bit difficult, since once you've added food to the salt to the food, it might be difficult to add more salt, since you have to take the food back to the state where it was before you add the salt. But maybe you can make the food the same way, and then you can still reproduce the experiment. And the other thing is, the hypothesis must be falsifiable. In other words, if I have added salt to the food, there is a chance that the food will taste worse. In other words, then I falsify my hypothesis, since clearly salt has not solved the problem. And now we will use this scientific method, these 5 steps, to describe and analyze algorithms. So that's what our aim for this lecture is. So why do we want to analyze algorithms? Well, the first obvious one is that we want to predict the performance of the algorithm. And there we have a couple of questions. Now, of course, it's not so easy to answer the question, will my program finish? In fact, if you want to answer that question in general, whether my program will finish or not, then you will realize that that's one of the problems that a computer cannot solve. In other words, you cannot write a program and give that to a computer and say, will my program finish, by using another program to check that. But of course, if you analyze this program maybe by hand, you can realize that this program might finish or it will not finish. Also, the other question is, when will my program finish? I mean, if you are Google, for example, you actually want to have a bound on when the search will take place and when the user will get the result. So in that sense, it's important to answer the question, when will my program finish? Of course, if you have this measure of analyzing algorithms, you can also compare the algorithms. So you could ask questions as, will this change make my program faster or slower for that matter? Or you could ask the other question, how can I make my program much faster? And then of course, if you have a way of analyzing algorithms, it will allow you to create new technology, it enables new technology, and it will also enables new research, not necessarily both at the same time, but this is the kind of things that you can do when analyzing algorithms. So let's look a bit back in the past and see if things that has succeeded where it enables new technology when we start analyzing algorithms. Now, the first example is sorting. So sorting is when I have a bunch of n items that can be strings, integers, or whatever they are, and you want to arrange them in either ascending order or descending order. You could think of many places where you want to use that in databases, in scheduling of events, statistics used it a lot, genomics used it a lot. I mean, without that, things such as eBay, Google, Amazon, they all have big databases that would not have existed. Now, if you look at it and you count the number of steps that the brute force way would use to solve this problem, remember brute force that's sort of the straightforward way, you don't think about it clearly, you just do it, that would take n square steps. So just to make sure, if I have n items and I count the number of steps, it would take n square steps. However, in 1945, John von Neumann, and he is also a very famous computer scientist, in fact, he is accredited also with the design of the computer as we see it today. In fact, we still use what we call the von Neumann architecture for computers. If you continue with computer science, you will learn in computer science 244 next year, or whenever you take it, you will learn about the von Neumann architecture in more detail. But he also invented the algorithm merge sort, and that's a fancy way of sorting items. And if you have an array of n items, that would take n log n steps. And indeed, without this new technology, companies such as Amazon and Google and eBay would have been out of business if we didn't have this faster algorithm. On the plot there, we actually have some graphs of what it means if we have different running times for algorithms. We will discuss it in detail, but you can see that the quadratic way of solving this, and that's this n squared thing, we classify this quadratic, that takes much longer if we increase the sample size, the size of the array, than it would take with this linear, or in this case what we call linear rhythmic solution. The other example that we have is the discrete Fourier transform. Now, I don't want to give the complete detail about the Fourier transform, but it is a very important technique also, and it's used almost everywhere. If you have a cell phone, there will be a discrete Fourier transform, many of them implemented on the phone, since I mean they form the basis of analyzing the frequencies in waves. You use them in compression. For example, the JPEG algorithm used the discrete Fourier transform in order to compress JPEGs. If you play music, your MP3 player use some form of the Fourier transform to compress the music so that you don't have big files, and then they play that back and you have nice music again. Also, to get rid of noise in your music player, the sounds usually have some filters that you have to get rid of sounds that you don't want to hear. For this, they also use the Fourier transform. So it's really used everywhere. Again, if you implement the Fourier transform in a brute force way, it would take n square steps. However, if you implement what we would call the fast Fourier transform, the FFT algorithm, then indeed that would take only n log n steps. And this is again the moral of the story. Without this new way, this ingenious way of solving this problem, we would probably not have had today an iPod, a PlayStation, a camera, or any of those fancy things that we are so used to today. So to solve and answer all these questions, what I'm going to do for the rest of this lecture is to make one example, and then from this example we will analyze this example in detail to show all the principles that's hidden or that's into play when we analyze algorithms. And for this particular example that we're using is a so-called threesum problem. So in the threesum problem, I give you n integers, and then the question is how many triples sum to 0. So for example, if I give the numbers over there, I specify them in this file, then I should check all the triplets that I have there. How many of them will sum to 0? So minus, I must now find a suitable one that will work here. So 30 plus minus 20 plus minus 10 is, for example, an example that will sum to 0. And so that's the question that we have. In fact, there are the results that I have over there. Those are the 4 triplets that in this scenario would sum to 0. It's not just a stupid problem, this one. It's an easy one, but it's deeply related to problems in computational geometry. So let's write down an algorithm to solve this problem, and that's the one that I show you there on the slide. So this is the brute force solution, and that's the one that we will do now. So let's go through it line by line. So we want to count the number of triplets for the array A. So n here is the length of the array, so there are n entries in this array. And then to start with, we say that there are 0 triplets that sum to 0. Now we make all the possible triplet combinations that I have over there. So I iterate through the array, or through all the items in the array, and for each item in the array I check all the other items that I can pair with it, and for those two I pair again the third pair I get. So it's important to make sure for yourself, if you watch this as a video now, of course you watch the video since you listen to me, then I would suggest that you pause the video at this stage and make sure that you understand how these 3 loops allow you to get all the possible triplets in this array A. And what we do then is we compare the triplets that I currently have, these 3. If they're equal to 0, their sum, then I would increase the number of triplets, the count of triplets, and otherwise I would not. And then once this is finished, I will return the number of triplets that I found in this array that sums to a 0. And then the way we will run it is we will just read the values from the command line, and then we will run this and print out how many times they would do. So it's in a sense a really easy problem that I have over there. Now we want to analyze this in detail. So the first step that we want to do is we want to do this empirically. In other words, we are going to do some measurements. And I'll start off by showing the idea of what I want to do. So I've implemented this, of course, already. That was not the plan to show you that I just crashed my computer. There it is again. So I open the file again, threesum.java, and if we give it a minute, we will see it. It's just the code that was on the slide. I just have the count there, and that's the method that we are going to test. And so I have a couple of files here. So 8 ints contains 8 integers. Then I have some others there. There's 1k int, that is 1000 in 24 ints. 2k is double that, 4k is double the previous one, 8k is double the 4k. I'm not going to print it out here, since I mean that would just be a bunch of numbers, not interesting. So what I could do is I could run my program. So let's run it with the 8 ints. And then you will see, it takes 0 seconds. Now it's not entirely 0, but that's so fast that the computer cannot really time it. So it will say it's 0 seconds. Then I run it maybe for the 1000 integers that I have, actually 1024, and that takes 0.977 seconds. And then I can run it maybe for the 2048 integers, and that would take a bit longer, so let's give it a time, and I'm not sure, it will probably take another second or so, and it takes 7 seconds. Now I'm going to run it for 4 as well, but it will take much longer, and I mean it's not really that interesting to watch that. But the question is now, if I run it for 4k ints, can you predict how long will that take? Or for 8 or for 16k ints? How long will that take? And that's basically the kind of question that we want to answer. Sorry, that's the wrong slide. So what I have here is, in a sense, this table over there. And in this table, what I show then is I record for 512 integers how long it is, for 1024, and so forth, and I write down the time. And so I want to analyze these values. Now I should say one thing, and if n, the number of integers, is too small, then the measurement that you will get here is not really meaningful. It will contain a lot of noise. So it's usually better to make it slightly larger, like 1024 in this case, being able to do this. But before I analyze this, I actually want to ask the question, how can I actually get these times? And for that, I have here a class, stopwatch.java. And so we also have now some opportunity to look at our object-oriented way of programming again. So let's look at this code. So what this stopwatch does, it declares some immutable private instance variable start. And when you construct this stopwatch, it will record the current time milliseconds of the system in start. Now remember, this function call will return to you the number of milliseconds that have passed since 1970. And then when you call elapsed time, you take a snapshot again, so you get the number of milliseconds that have passed since 1970. And of course, if you subtract the one from the start, divide by 1000, you get the number of seconds it takes since you've created the stopwatch. And so basically, essentially what we will do is we will write code where we create a new stopwatch, and when we have created the stopwatch, then it will start counting, and then we can say get the elapsed time, and that would give you then the time that was elapsed since you've used created that stopwatch. And I open all the wrong windows. Let me find the right one. So just, I think I also have from the slides again the stopwatch. That's the idea. We count it, and that's the class. How we would do it, the API, but you've just seen it in the code. And this is the way we will use it. We create an instance of the stopwatch, and then we do whatever we want to do, and once we've done that, we say, okay, print for me out the elapsed time. Okay, so remember what we're actually trying to do is we're trying to analyze the algorithm that I've shown over here, this threesum. So let's go and do that. And so what we can do is we can plot this running time for different input sizes. So yeah, for 1k it takes a certain amount of time and until this one. And now the question that we have is how does this grow as a function of n? So if I give you the size n, can you predict, in other words, how long this program will execute? So we will make some hypothesis, and the hypothesis that we make is if we say that some power law is obeyed. So the running time approximately obeys a power law, and it is this particular one that we have over there. So what we could do is we could then plot this, and this is indeed what we're doing here, not on a normal scale, but we plot this on a log scale, a log scale. We plot then the running time. I really hope that you've done at this point log plots. If not, you should now at this point pause the video and make sure that you know what the log scale is. But basically you can see there is we just do it in, we take the log of numbers, so this grows as the logarithm of the numbers, and this way as well. So it's, we can really plot a lot of things on this axis. So this is then a log over there and the log over there. So we take the log on this side and the log of that side, and that's what we're plotting. And indeed, if you do that, you get the running time, this b constant, as the slope of this line. Just to make that mathematics more clear, so if I have Tn, this is the one that I have at the moment, Tn is equal to a n to the b, then I take log on both sides. So I have log of Tn equals the log of a n to the power of b, and hopefully you still remember from high school that the log of a n b is equal to the log of a plus the log of n b, and that's equal to the log of a plus b, the log of n. And now you can see this just looks like it. Remember, we plot in this scale, on the log scale. So this is almost like a line y equals c plus mx, and this m of course is your slope of the line. And so you can get the, if you have the slope of the line in the log domain, you actually have this b value that I have over there. So if we get back to my slides, you will see that indeed if you plot this for the data, you will see that the slope is there 3. And so now we say that the running time of our algorithm is of the form a n to the 3. So look how the scientific method is at play. We started off saying we think it's a power law, so Tn a n to the b, and now we say, okay, but maybe this b is not just any random b, it's in fact 3. Now the question is, how do you get this b easily? You can just plot this thing, but there's actually something else we can do, and that's the so-called double hypothesis. So what we do is we run this thing for a size n, and then we double that size, so we run it for size 2n. And then by doing that, we would be able to easily calculate this value b that I've just mentioned. So if you run that, you run it for size n and for size Tn, and then you calculate this ratio between size 2n and size n. So let's do this in maths. So I have 2n over Tn. So I run it for size n and over size 2n, and I calculate the ratio. Remember, I can calculate this is the number of time. I can have this number of seconds there. I have the number of seconds. I divide this and I get this ratio. Now, of course, in this case, we have the hypothesis that t to the n is of this form, a to the power of a n to the power of b, and then of course this one would be a to n to the power of b. The nice thing is this thing just get wrong, get cancelled out, not wrong, it's just cancelled out. This n and this n cancel out, so you have 2 to the power of b. So this constant, let's call this a constant, that this division equals to c, and this is the ratio, and that's equal to 2 to the power of b. So in other words, to get b, we can just take the log on both sides. So the log of c is equal to b. Now I should just mention this, since maybe some of you are now saying, what on earth is going on? So remember, in mathematics, log can have a base number over there. So you can have log 3, and the base of the log is in this case 3. We have the log b, or even log e. Now what we will do in computer sciences is, if we assume that this is not playing a role, remember this is just a constant, you can always cancel that, divide it out, and it's just a constant factor. Then we'll just write down log if we don't care about this number over there. If we want to specify that it's indeed with a base of e, then we will just use ln. And if we have 2 there, then we will use this notation, lg, to mean log. But just back to my example, so in other words, if we have this ratio by using this doubling hypothesis, you can easily calculate this b. So let's put this into questions. So my first question that I want to ask you is, let Tn be the running time of a main as a function of input size n. Now in this scenario, T2n divided by Tn, that ratio converges to about 4. My question is, what is the order of growth of the running time? Now if you watch this video at this point, I want you to pause and work that out. And the answer to this question would be n squared, so n squared. If you don't get n squared, you should work it out until you get that answer. I have a second question. So let Tn be the running time of main as a function of input size n again, and now Tn over Tn, T2n over Tn converges to about 2. And the question is, what is the order of growth of the running time? Again, pause the video at this point and then answer the question. And just to help you, the answer of this question would be n or n log n. It's not written there, but that can also be an answer to this question. So now the question is, well, we have now this case over there, that we can run this, and how do we estimate this value of a? Since we have a way of estimating this b value over there if it's a power law, but how do we estimate a? And it's easy. What you do is you just run this program. You run it multiple times, and once you've done that, you can calculate this by solving this equation over there, and then you can calculate the that constant. So now you have a refined hypothesis, and the refined hypothesis says the running time of this algorithm is about 2.5 times 10 to the minus 10 times n to the third 3 seconds. And the nice thing about that is now I can tell you that n is 16,384, and you can go and calculate how long that will take to run this program. And so if we do this, we predict this for this particular machine, that will take 1,100 seconds, and then we actually go and run it, and we get to 1,118.86 seconds, and that's really close to this thing. The nice thing about this is I mean, if you work in rocket science, if you do these kind of predictions of how a rocket will fly, you have to find a place where you can launch a rocket in order to make your prediction. If you work in car manufacturing and you predict how your car will crash, you actually have to do a crash test at this point. The nice thing, if you work in computer science and you make these predictions, you just go and run a program. Nothing more you can do. You can actually validate and run your own experiments. Isn't that nice? So, remember, I've done now a analysis on empirical analysis. So what I want to do next is to do some mathematical analysis. And again, the person who's responsible for this, I've mentioned him before, he is Donald Knuth. In fact, he won the Turing Award. By now you should know what the Turing Award is, in 1974. And now when we look back, the ideas of Knuth actually sound kind of obvious. But you should remember that in the 1960s, computer programmers said that it would be impossible to do these kind of things. It would be impossible to do these kind of predictions. And then Knuth just say it's possible, and then he also show how it's doable. In fact, Knuth is also known for many other things. He has written this classic in this field, a set of books, The Art of Computer Programming. He's a very good an author, and so if you have time, just go and get the books. I think they are actually in our library. He's also the inventor of TEG, and maybe at some point you will learn LaTeX and TEG as part of your university career. So what we want to do now is we want to do some mathematical analysis of our program. So what's the key insight that we want to have here? Well, the key insight is we want to count the number of times that the instructions take place. So let's look at an example. And the example that I have over here is just a loop that check how many elements of an array is equal to 0. So I start, count the number of them is 0, and I go through the arrays. Now I can go and count the frequency of all the things going on here. So I have a variable declaration over there that will go execute once, and this will execute also once, so I have 2 in total. I have an assignment, so I assign over there, I do an assignment over there, so I do 2 of them. Then I have this less than comparison over there, and I do this, of course, n plus 1 times. So for the n times of the loop, and then one more time to realize I should not do the loop. The equal comparison, well, that I will do n times since there's n elements in the array. The array access, of course, every time I want to compare this to 0, I have to access the array. And then this increment operation, well, how many times will I do this? Well, it depends only when I actually increase this. So if ai is equal to 0, then I will increment. So that should be smaller than 2n, but not more than that. Let's do another example. So in this case, I have 2 elements in an array. I want to check if 2 elements in an array sum to 0. So it's not a 3-sum problem. You could say this is the 2-sum problem. So I go through all the elements in the array, and then in all the elements in the other array, although I start one element after I, and then if those 2 elements adding up to 0, I increment count. And I do the same thing. So how many variable declarations do I have? Well, I have 1 over there, 1 over there, and then this loop is executed n times, so I will declare n more j variables. So I will have n plus 2 variable declarations. Similarly, for this assignment, we will have n plus 2. Now things get a bit tricky, since I have this less than comparisons over there. So how many of them are there? Now we can count them exactly, and it's this number that I have over there, half n plus 1, n plus 2. What I would suggest at this point is that you go and derive these equations for yourself. Otherwise, what you could do is you could assume this to be true, and that is true, and then you can prove by mathematical induction, which I hope that they teach you in mathematics. You can prove that this is the right number of array access, or equal to comparisons or less than comparisons for this case. At some point later this semester, I will also do a couple of proofs and show that to you. For the moment, if you can't see how to do this, just believe that if we count this, it will actually be that number. So again, so what have I done so far? I'm just counting the number of times that things happen. So I count the number of instructions, the number of operations that takes place, and I write down as a function of n how many times it happens. Now for this to work, well, not to work, but we could always go and do this counting and write down an exact number, but we want to simplify this thing to give sort of an easier answer to this question of how many operations there is. But in the same way, we don't want to lose the explanatory power of what we're trying to do. And to accomplish this, we will use the so-called tilde notation. So what the tilde notation does is it's sort of forming an estimate for a function as of n, of input size. And what we do is we ignore the lower order terms. Since when n is really large, then the lower order terms will be small compared to the large terms, and so we can just ignore them, since it will basically dominate, it will be dominated by the higher order terms. However, if n is small, well, we don't really care about that. Then it will take a second, a couple of milliseconds, a couple of nanoseconds to execute the program, and so we're not really interested in that case. So let's see how the tilde notation works. Say, for example, I have a growth function in this format: 6n to the power of 3 plus 17n squared plus 56. Then I would say that's in tilde notation, so tilde equal to 6n cubed. So I throw away this one and this one. Remember, this equation comes down from this kind of analysis. I count all these things, operations that takes place. That's the key in start. I count the number of things takes place. Then I add up all these things. And when I add them all up, I will get something like this, maybe this one. If I have this one over there, again, these are the lower order terms. I throw them away. In this case, I also have some lower order terms. I throw them away, and it's 6n to the 3. And just to see why this is relevant, I mean, if n is 1000, then this 6n to the 3 will equal 6 trillion. And this term would equal 169 million. And clearly 169 million is really small in comparison to 6 trillion. And that's why we just throw that away. From a technical point of view, I can have a definition for the tilde notation, and I have it there. So f of a function of n, tilde gn means that if I divide gn by fn, and I let approach n to infinity, so I really have large n, then that will be equal to 1. So I think we have now moved to a point where you should understand the number of operations that takes place, how I count them. Remember, I've done the empirical analysis, and what I do now is I say, okay, I want to do it in the mathematical framework. The key insight for the mathematical framework is that we count the number of operations that takes place. We then get an equation for this, and from this equation we have this as a function of n. Then I said, well, it's too difficult to, or I want to simplify this. Not necessarily difficult, I want to simplify this. I still want to explain things, but I want to simplify this, and for this I use then the tilde notation. And what does the tilde notation? I throw away the higher order terms, and I keep the higher order terms, and I throw away the lower order terms. So what I want to do next is I want to discuss how we do this kind of analysis on our threesum problem, the one that we've done so far with the empirical analysis. But this will be the topic of the next video lecture. Thank you.